Welcome to a fascinating journey into the future of construction. Today, we're exploring a groundbreaking innovation from the Netherlands that could transform our cities: self-healing concrete infused with fungi. This isn't science fiction. It's happening right now in laboratories at the Technical University of Delft, where Dr. Henriette van der Meer and her team are pioneering a living building material that could dramatically reduce carbon emissions while creating structures that repair themselves. Join us as we discover how the ancient biology of fungi is being harnessed to solve one of our most modern challenges. In the laboratories of the Technical University of Delft in the Netherlands, Dr. Henriette van der Meer and her team have achieved something remarkable: concrete that can heal itself using fungi. This innovation represents a convergence of mycology, materials science, and civil engineering in ways that were barely imaginable just a decade ago. As Dr. van der Meer explains, we're essentially creating a living material. The mycelium network remains dormant within the concrete matrix until microcracks form, at which point moisture activates the fungi to grow and deposit calcium carbonate, effectively sealing the cracks before they can compromise structural integrity. This living concrete, dubbed Mycocreate, functions almost like a biological immune system, responding to damage automatically and without human intervention. This innovation arrives at a critical juncture in construction history. For centuries, the building industry has relied on a linear model. Materials are extracted, processed, deployed, and eventually discarded, an approach increasingly at odds with environmental realities. Concrete, despite its versatility, has remained fundamentally unchanged since Roman times when they perfected their pozzolanic cement mixture over 2 millennia ago. The incorporation of living fungal networks represents perhaps the most significant paradigm shift in concrete technology since the development of reinforced concrete in the 19th century. It challenges our very conception of what building materials can be, moving from static, dead materials to dynamic, living systems capable of adaptation and self-repair. The process begins with carefully selected fungal strains, primarily from the Trichoderma and Aspergillus genera. These particular fungi were chosen for two critical properties: their resilience in highly alkaline environments like concrete and their ability to precipitate calcium carbonate, essentially creating limestone. These fungi are cultivated alongside specialized nutrients, then introduced to the concrete mixture in a dormant state. The mycelium, the vegetative part of fungi consisting of a network of fine white filaments, remains inactive until triggered by specific environmental conditions that indicate damage to the concrete matrix. When microcracks form and moisture enters, the fungi awaken, grow into the cracks, and deposit calcium carbonate, effectively healing the damage before it can spread and threaten the structure's integrity. This mimics how living organisms heal wounds, bringing a biological process to what has traditionally been an inert building material. What makes Mycocreate particularly significant is its environmental impact. Traditional concrete production accounts for approximately 8% of global carbon emissions, more than the entire aviation industry. The fungi-concrete hybrid not only reduces the amount of traditional cement required but actively sequesters carbon throughout its lifetime. Research published in the Journal of Advanced Sustainable Materials demonstrated that structures built with Mycocreate could sequester up to 20 kilograms of carbon dioxide per cubic meter annually for the first 5 years after construction, effectively transforming buildings from carbon emitters to carbon sinks. This carbon sequestering mechanism works through a fascinating biological process. When activated, the fungi not only deposit calcium carbonate to heal cracks but also incorporate atmospheric carbon into their growing biomass. This carbon remains locked in the material even after the fungi return to dormancy. Additionally, the presence of mycelium networks enables a reduction in Portland cement content by up to 30% without compromising structural integrity, thereby further reducing the carbon footprint of construction. Environmental engineer Dr. Sophia Chen from Stanford University, who conducted an independent life cycle assessment of Mycocreate, notes that, if implemented across just 15% of new concrete construction globally, this technology could offset carbon emissions equivalent to taking 8 million cars off the road annually. Unexpected collaborations have accelerated the transition from laboratory curiosity to practical building material. The Singapore Urban Redevelopment Authority has partnered with van der Meer's team to construct a 400 square meter pavilion using Mycocreate as a proof of concept structure. Completed in February 2023, the pavilion is equipped with hundreds of sensors monitoring structural integrity, carbon sequestration rates, and mycelial activity. What's fascinating is how this technology connects ancient biological processes with cutting-edge construction needs, notes Dr. Arun Patel, a civil engineer monitoring the project's progress. Fungi have been building complex structures for hundreds of millions of years. We're just now learning to speak their language. The Singapore pavilion has already weathered 2 monsoon seasons with remarkable resilience. Microscopic examination of core samples taken from the structure reveals extensive networks of calcium carbonate deposits precisely where hairline cracks had begun to form, visible evidence of the self-healing process in action. Perhaps most surprisingly, the building maintains a more stable internal temperature than control structures made with traditional concrete, suggesting unforeseen benefits for energy efficiency. Construction giant Buoy Construction has now launched pilot projects in 3 different climate zones: Helsinki, Dubai, and Jakarta, to test the material's performance under varied environmental conditions. Early results suggest that the fungi actually adapt to local conditions, with different growth patterns emerging in response to specific environmental stressors, a form of material intelligence previously unimaginable in construction. In the freezing temperatures of Helsinki, the fungi have developed patterns that provide better resistance to freeze-thaw cycles. In the extreme heat of Dubai, the mycelium networks form different structures that help maintain material integrity despite thermal expansion. And in the humid conditions of Jakarta, the fungi demonstrate yet another growth pattern optimized for constant moisture and tropical conditions. This adaptability suggests that Mycocreate isn't just a single material but rather a platform technology that can be customized for specific environmental challenges. Despite its promise, Mycocreate faces significant hurdles before widespread adoption. Building codes worldwide must be updated to accommodate living materials, and questions remain about long-term performance in extreme environments. Regulatory frameworks designed for inert building materials struggle to categorize substances that blur the distinction between construction materials and living organisms. The International Building Code Committee has established a working group specifically focused on bioreactive construction materials, with preliminary guidelines expected by 2025. Meanwhile, insurance actuaries are developing new models to assess risk and longevity for structures incorporating biological components. These challenges highlight how truly innovative Mycocreate is. It doesn't merely improve existing materials but creates an entirely new category that our regulatory systems weren't designed to handle. The process of updating building codes, insurance models, and construction standards represents a significant hurdle, but one that stakeholders across the industry are actively working to overcome. Perhaps most intriguing are the unexpected applications emerging from this research. Archaeologists at Universidad Nacional Autónoma de Mexico have begun experimenting with similar technology to stabilize ancient Mayan structures without damaging their historical integrity. Meanwhile, NASA's Habitat Technologies division has expressed interest in adapting the technology for potential Martian construction, where importing traditional building materials would be prohibitively expensive. Beyond construction, the research has sparked interest in other fields. Biomedical researchers at Imperial College London are investigating whether similar principles could be applied to create self-healing medical implants. Meanwhile, acoustic engineers have noted that the unique internal structure of mycelium-infused materials demonstrates exceptional sound dampening properties, potentially offering new solutions for urban noise pollution. The economic implications are equally profound. A 2023 analysis by McKinsey & Company suggests that widespread adoption of self-healing concrete technologies could reduce global infrastructure maintenance costs by up to $400 billion annually by 2040. For rapidly developing regions with limited maintenance budgets, such technologies could transform infrastructure planning. This development represents a broader shift in engineering philosophy toward biomimicry, the practice of emulating nature's time-tested patterns and strategies. Dr. Janine Benias, who pioneered the field of biomimicry, sees the fungi-concrete hybrid as a perfect example of this approach. For centuries, we've treated buildings as inert objects that inevitably degrade over time, Benias observes. Natural systems don't work that way. They're dynamic, responsive, and often self-healing. Mycocreate isn't just a new material. It represents a fundamentally different way of thinking about our built environment. The mycelium networks in Mycocreate bear striking resemblance to how neural networks function, distributing intelligence throughout a system rather than centralizing it. This distributed intelligence allows the material to respond differently to various types of damage, prioritizing structural cracks over surface abrasions, for instance. Some researchers have begun exploring whether more complex programming, of these networks might be possible, potentially creating materials that could respond to multiple environmental cues beyond just moisture intrusion. Perhaps most profound is how this technology challenges our conception of what a building is. We're moving from an era of static architecture to one of dynamic architecture, explains architectural theorist Dr. Maya Lin of Columbia University. Buildings need no longer be the end products of a construction process, but rather the beginning of a biological one. As climate concerns intensify and urban populations grow, the humble fungus, neither plant nor animal, may prove to be an unexpected ally in creating more sustainable, resilient cities. The technology serves as a potent reminder that some of our most pressing modern challenges might find their solutions in biological systems that have been perfecting their craft for millions of years before humans first stacked one stone upon another. As Dr. van der Meer puts it, we're not just building with nature, we're building within nature's paradigm, creating structures that are less like artifacts and more like organisms. The future of construction may well be cultivated rather than constructed. This vision represents not just a technological breakthrough but a philosophical shift in how we understand the relationship between our built environment and the natural world. From the laboratories of Delft to construction sites around the world, the fusion of fungi and concrete represents a profound reimagining of our built environment. Mycocreate isn't merely a new building material, it's a new relationship between humanity and our infrastructure. By embedding living systems into our buildings, we're creating structures that grow, adapt, heal, and even breathe, transforming them from passive objects into dynamic participants in our ecosystem. As we face the dual challenges of climate change and urbanization, this technology offers a path toward buildings that improve with age, sequester carbon rather than emit it, and respond intelligently to their environments. The implications extend far beyond construction, from archaeological preservation to space exploration, from medical implants to noise reduction. What began as an unlikely partnership between mycologists and civil engineers has blossomed into a vision for cities where the line between the built and natural environments begins to blur. In the words of Dr. van der Meer, we are learning to cultivate rather than construct our world. And in doing so, we may have found a powerful ally in one of Earth's oldest and most sophisticated organisms. The humble fungus, it seems, may help build our future. Thanks for watching. Please like, subscribe, and hit the bell icon for updates. Your feedback is appreciated. We hope to see you again.